In a previous video, we looked at identifying the maximum or minimum when we're given a quadratic equation or when we're given a graph. Something interesting happens when it falls on the x or y axes. When the maximum or minimum falls on the x or y axes, we can see interesting patterns that fall in how we identify the quadratic equation. We're going to learn about what these patterns are. So when we're given a quadratic equation and we see the pattern arise, we can immediately identify where the maximum or minimum occurs on the x or y axes. Or if we're given a graph and we see the maximum or minimum fall on the x or y axis, we can quickly identify the quadratic equation. The simplest case when we look at the maximum or minimum falling on one of the axes is when it falls on both axes. So when the maximum or minimum falls at the point of intersection of the two axes, then we can see that the quadratic equation just falls out to be y equals ax squared. So why is this? So the point that the two axes intersect is at the 0, 0 point. We also call this the origin. And we can see that the c constant goes to 0 by just plugging in x equals 0. So these two terms drop out, and then y equals 0. So then we get 0 is equal to c. And then we also can see that the b term goes to 0 if we plug this in the 0, 0 point as the derivative. So remember, the derivative is dy dx is equal to 2ax plus b. So if I plug in x equals 0 at the max or min, then dy dx equals 0 is equal to b. So then b goes to 0. So we're going to take a look at a couple graphs where we just look at y equals ax squared and identify that the maximum or minimum just occurs at this origin. So here's my general graph. And there's the point of intersection of the axes, and that's my origin. And so all the graphs that we're going to show are either going to have a maximum at the 0 point or a minimum at the 0 point. So just take a look at the equations and see what kind of patterns you observe. So there's the easiest, the simplest graph. So a is equal to 1, so y equals x squared. That's the one that we usually start with. We can flip it across the x-axis by putting a negative sign, right? So now we have a maximum here instead of a minimum that we see from y equals x squared. If I change the constant here, but keep it positive, it's still going to be a minimum like x squared is, but it's going to have a different shape, but it's still going to be symmetric across the y-axis. And if I put a negative sign in front of that half x squared, then we get it mirrored across the x-axis again. And then we could put different constants as well. So you see the pattern, right? So if you see a maximum or minimum crossing the origin, anything that looks either like this or like this, you know that your equation is going to be y equals ax squared, and there's not going to be a b term, and there's not going to be a c term. And then you also know that if it's positive, or if it's giving you a minimum, that the a value is going to be positive, and if it's giving you a maximum, that the a value will be a negative term. It's also very good to use y equals negative x squared or positive x squared, so a equals plus or minus 1 as a reference point. So when you're looking at your a terms, you either are tighter in if the value is larger than 1, or you're more open, like these, the 1/2, the green graph is showing you here. So you can have a reference point of either when you're given a graph, are you larger or smaller than 1, or if you're given an equation, whether you're going to be wider or skinnier than the y equals plus or minus x squared curve. So we looked at the case where the maximum or minimum falls on the origin, the 0, 0 point. Now if we take it off the origin, but keep it on that y-axis, keep it on that vertical axis, now our c term does not go to 0. Our b term still goes to 0, and we can see that again with the derivative. dy dx is equal to 0, is equal to 2ax plus b. Well, your x term along the y-axis is still 0, so your b term will go to 0. But your c term will not go to 0, and we'll look at what happens to this c term by looking at some graphs again. So here we have y equals x squared. That's my reference graph. And then in blue, I have y equals x squared plus 1. And y equals x squared plus 3. So we take the graph. The shape of the graph is staying the same, but we're shifting it. And how much are we shifting it? We're shifting it by whatever we have as our c value. So for this blue graph, we see that the minimum point is 0, 1. So x equals 0, y equals 1. And for this red graph, we see that it's occurring at 0, 3. So at a y of 3. So we do see that when we're on the y-axis, the c value of the quadratic equation is equal to the point that we have a minimum. We can also see what happens when we have it as a maximum. So negative x squared is my reference graph. Then I put negative x squared plus 1, so that's my c value is 1. And negative x squared plus 3, so my c value is 3. And that still matches. So even if there's a negative a value, the c value is the point of intersection on the y-axis. We can shift this down and it doesn't matter, it's the same thing, right? So if I put negative 3, negative 1 as my c value instead of positive 3 and positive 1 previously, right? So this graph just shifts down negative 1, shifts down negative 3. So it's still c is equal to wherever your maximum or minimum is occurring on the y-axis. And again, if it's a maximum instead, negative x squared minus 1, negative x squared minus 3. Same process. So when the max or minimum falls on the origin, we saw that b and c are equal to 0. When the max or min fall on the y-axis, we saw that b is equal to 0 and c was wherever the point of intersection on that y-axis was. When we have the max or min fall on the x-axis, it's a little bit more complicated. We're going to have a, b, and c terms be non-zero. We're going to see how to identify it. It's a little bit more complicated, but the concept is the same in terms of how do I identify where y is equal to 0, right? Because when we are on the x-axis, y is equal to 0 the whole way through, right? So let's take a look at our graph and show our general graph y equals x squared, right? So here we have b equals 0 and c equals 0, and it's falling at the, we're most interested now on where it falls on the x-axis. It falls on the 0 point on the x-axis. Okay, so that's fine. B and C are equal to 0 when x is equal to 0 for the max or min. So here we show it. So when we're on the y-axis, I took my y equals x squared graph and I shifted it up and down this y-axis. Now, instead, I'm shifting it left and right of this x-axis. Okay? So the graph shape is the same because they're all having a is equal to 1. But there is a non-zero b term and a non-zero c term. So right now we have what? Y equals x squared minus 6x plus 9. That's this graph right here. That has an intersection of 1, 2, 3 of x equals 3. It might not be apparent right now, but looking at this equation, we should be able to identify that we would get an intersection at x equals 3. Here we have x squared minus 2x plus 1. We should have an intersection at x equals positive 1. And then if we change the signs of our b term, right? So right here is x squared plus 2x plus 1. So just the sign changed here, we would get a negative 1 intersection. and over here we would get a -3 term intersection. So why is that? So we can change the way that this equation looks like, and it'll be a lot more apparent. So if I change my equation from y equals ax squared plus bx plus c to y equals x minus d quantity squared, I can expand this equation here, and we get y equals x squared minus 2x times d times negative d squared, or just positive d squared, right? So this is just, you've done this before, right? I think you might have seen this as a minus b squared is a squared minus 2ab plus b squared, right? That's the same form, just expanding it. So what does that mean? Well, if I just look at this equation here, y equals x minus d, where d is some kind of constant squared, I know where it would intersect on the x-axis. Because if I make x is equal to d, then this y term will go to 0. So if it's in this expanded form, as long as I can identify what d is, I can see where it would intersect. Okay? So I can write this as positive d, but this is basically, when does this intersect? This intersects at negative d. So you can really just use one form, but it might be easier to look at these in both of these forms. So if I rewrite these equations in this form, the x minus d squared or x plus d squared form, what do we get? Right, so let's look at this red one first. X minus 3 quantity squared is x squared minus 6x plus 9. So these are the same equations. But if I give you the equation in this form, you can quickly identify that if x equals 3, y equals 0. So that's why it's the minimum is occurring at 3, x equals 3. Here, the minimum is occurring at x equals positive 1. Here, the minimum is occurring at, the minimum is occurring at x equals negative 1 and at negative 3. Does that make sense? All right, and then we can flip it. And if I want to flip it, I know that my a term needs to be negative, right? So it needs to have a negative x squared. So how do we do that? We just put a negative sign in front of these terms that's shown here, right? So instead of x minus d squared, we put negative x minus d squared. And then we'll have a negative x squared. This will be positive, right? Switching the signs. This will be negative, and so forth. And so let's take a look at what these graphs look like in negative form. Right, so now they have maximums. We literally just flip all these graphs. We got negative x squared as a reference, and then negative times x minus 3 quantity squared. We have negative x squared plus 6x minus 9 intersects again at x equals 3, right? Because x equals 3, y equals 0, and so forth. So you can see the pattern. So if you see a graph and it's falling, the maximum or minimum is falling on the x-axis, you identify what that is, and you can write it in one of these x plus or x minus d squared form. And if it's a maximum, as we're showing here, just put a negative in front of it. And if you see something where the c value is like the square of a value that's you look similar in the b term, then you might want to try to change it into this form to see if you can predict that there's a max or min on the x-axis. Okay, so now I want you to try to use the same methods to identify the max or min, or identify the equation when given a graph. And I'll give you a couple example problems in the next slide. Okay, so I have 7 problems here for you. In all cases, just to keep it simple, I've set a to be plus or minus 1. So it's going to be either plus x squared plus bx plus c, or negative x squared plus bx plus c. So all you have to do is identify the b and c term. In certain cases, I give you the graph, and just because it can be hard to read, I tell you the minimum or the maximum. Right? So here for this one, the minimum is 0, negative 12. This one, the minimum is negative 11, 0. This one, the maximum is 6, 0. And this one, the max is 0, 0. And for these four, I want you to identify what the equation should be using the tools that I just taught you. And then for these three, I give you equations, and I want you to see if you can sketch a graph. More importantly, can you identify where the min or max should occur, and is it a min or max? I'm not going to walk you through this process. I'll press pause, try to work this problem out, and then I'll show you the solution in a second. But definitely press pause now and try this problem out. Okay, so make sure you press pause, because I'm going to show you the solution now. I want you to check to see if you match the solution. All right, so here's a solution. If you don't match any of them, go back to the previous parts of this video to see how we identified the max or min either on the origin, as we have here, along the y-axis, as we have here, here, and here, or along the x-axis, as we have here, here, and here. So hopefully this makes sense. Identifying where the max or min occur on the x or y axes can save you a lot of time and speed the process up. There are also very specific engineering applications when we observe this, or we can change to make this observe, just to simplify the systems that we're trying to describe with equations, right? So we're going to take a look at that at the end of this series of playlists, and we'll also explore when we're not on these simplified forms, right? When we don't have the max or min falling on the x or y axes, what patterns can we still build off of the ones that we talked about in this video, so that we can identify the graph or the equation quickly.